Hi, this is Steve. My guest in today's podcast is Professor Tim Palmer. Tim is Royal Society Research Professor in Climate Physics, co-director of the Oxford Martin Program on Modeling and Predicting Climate. He was trained in general relativity theory at the University of Oxford, but changed fields into climate modeling and meteorology. He was elected a Fellow of the Royal Society, Commander of the Order of the British Empire. He won the World Meteorological Organization Norbert Gerbier Mumm International Award in 2006, the American Meteorological Society Carl Gustav Rossby Research Medal in 2010, and the Institute of Physics Dirac Gold Medal in 2014. He was also elected to the National Academy of Sciences of the United States of America in 2020. I say all these things just to give you the bona fides of Tim in his field of modeling and predicting climate. I went to Tim for this interview because I wanted a no-nonsense evaluation of the current status of climate models. What are the open questions? What are the things that we're least confident about? And I think we explored those issues quite thoroughly in our discussion. This was taped in 2020. However, the issues, the state of the field really has not changed much in the intervening 2 years. And so I consider it still an accurate description of the state of climate modeling. I hope you enjoy the interview.
So let me start. I always like to get some personal details before we get into the science. What was your path like from being a relativist to, I think, into weather prediction? You worked on weather modeling and then finally into climate. Maybe you could just describe that for us.
Well, yeah, I mean, it's a long story. I mean, I finished, let me start by saying, Einstein and general relativity were kind of a childhood ambition of mine to do some research in that area. I kind of learned about his stuff. I don't know how old I was, 12, 13, 14, and I just became kind of utterly entranced by it. So I'd set my sights at an early age to try to do a PhD in relativity theory, which I succeeded in doing, and then was faced with the difficult problem. Is this something I want to spend my whole life doing? And I guess I kind of decided I'd kind of got my childhood ambition out of my system because I had the PhD. I wasn't completely sure whether because it was so kind of abstruse and very difficult to communicate, I would say, to the person in the street. They'd all say, "Oh, gee whiz, you're doing black holes. That's fantastic. Tell me a bit more about it." And if I did, that would shut them up very quickly. I learned about weather. I didn't know anything about weather, but by a strange coincidence, I'd been working on a rather sort of, this is at the time when Stephen Hawking announced the very famous result now that black holes evaporate. They lose mass by quantum processes. But people were trying to understand how to understand this result. It kind of came out of a very complicated calculation he did. Anyway, I started working on a thing called the principle of maximum entropy production as a way to try to understand Hawking evaporation. And I met by chance a meteorologist, quite a sort of eminent meteorologist. And I kind of asked him casually, well, what's interesting in your field? And he said, completely unprompted, he says, well, people are trying to apply the principle of maximum entropy production to understand how Earth's climate works. So this suddenly made an enormous resonance. I thought, hell, this is two topics which you could hardly think are more unlike each other: Hawking, evaporation of black holes, and climate, which seem to be linked by this common kind of mathematical framework. So I decided to have a shot at. So I said, well, if I can get a job in this, maybe I can try it for a couple of years, and if I don't like it, I'll go back to theoretical physics. So I got a job at the UK's Met Office, their weather centre, where this guy who told me about the maximum entropy applying to climate, he worked. And yeah, I found I enjoyed it. And I worked there for many years. I spent a little bit of time at the University of Washington in Seattle in their atmospheric sciences department. And I spent a long time at the place called the European Centre for Medium-Range Weather Forecasts. And I guess one of the main things I've done over the years is to kind of change the thinking in weather and indeed climate prediction from a kind of deterministic concept to a much more probabilistic, and thinking about uncertainty as a kind of primary variable in prediction. So yeah, it's gone. The transition actually all transitions I've made have gone more smoothly than you might think at first sight, because in a way, and I always say this, now I'm a professor at Oxford and I'm hiring people. If people come with PhDs in mathematics or theoretical physics, even if they're from a different subject, it's actually not so difficult to transition, as long as you've got the enthusiasm and the kind of motivation to make that transition. If you have a PhD in string theory or, number theory or something like that, you actually have 90-something% of the technical knowledge needed. And the rest of it's just learning up some of the jargon and some of the sort of detailed processes.
Having jumped around in my own research work, I agree with you, but I often find that the most difficult part is convincing the people in that other subject that your opinion might be taken seriously, because they can always point and say, well, you're just a physicist. What do you know about genomics, or what do you know about AI?
Yeah, they probably do that they probably feel threatened and they're doing that as a defense reaction. But I find one great thing actually about weather and climate research is that people realize it's the kind of field where you only make progress, and we might talk about this a bit later. You only really make progress by working collaboratively and interactively, whereas in some of the more, say, theoretical physics stuff, there's a lot of, I want to be the best. I want to come up with a breakthrough theory. So there's a lot more kind of secrecy and privacy, I think, and perhaps a less of a willingness to interact. So certainly in climate physics, I think people really do embrace new people, new ideas, and new thinking. So that hasn't been, it's not a problem I've encountered very much.
Before we leave your personal journey, I just wanted to say that it's a common story for things like Einstein's theory of special relativity, and then maybe a little bit later, general relativity, to be what I call a kind of strange attractor for bright kids, because the idea is so fundamental. Like what is the nature of space and time, or what is the dynamics of space time? You can't help but wonder about those things as you're a kid, when you're just learning, if you're a bright kid, when you're just starting to learn about time, for example. And so it attracts people, it's not, I think what you said is not uncommon for someone to say, wow, this general relativity thing is so amazing. I just would like at some point in my life to understand this. This is a monumental achievement of the human mind. And it's actually true. It describes the universe. So it's not, to me, not an uncommon way that people get sucked into physics.
Yeah, I actually spent a whole year in undergrad doing tensor analysis, and basically because of an attraction general relativity. I eventually didn't do anything with it, but I totally agree with you. It's not just the idea, but it's just the results are so beautifully counterintuitive initially that I think you can't help but just be fascinated by it, because your initial intuition is Euclidean. And when you're told that the world doesn't work like that, it's sort of mind-blowing.
Yeah.
I think even for non-technical people.
Yeah. However, if I could just make an important point that comes out of all this discussion, and I had this point, I discussed this with some of my colleagues in the climate field, because they published a kind of a commentary or something I think it was in Nature a few years ago, some quite sort of eminent colleagues of mine. And they were kind of bemoaning the fact that indeed the brightest, theoretical physics student or mathematics students, would go into things like, string theory or cosmology or number theory or, maybe GR and stuff like that. And, the question that they raised in this commentary is, well, what can we do? Given climate is such an important problem these days, what can we do to make climate a more appealing field for these people? So they, instead of, in choosing black holes or the Big Bang or something, they would do something on the cloud feedback problem, say in climate change. And I said to my colleagues that you're thinking about this completely the wrong way. When I was starting my PhD, if you had said to me, oh, I don't think you should do this, I think you should go into a much more practical field and start, doing weather forecasting or something, I would have told them to go away. I said, look, I'm not interested. Just go. Don't even think about it. It's a non-starter, because I've set my sights, from age 12 to do this, and that's what I'm going to do. But what happens, as I say, when I finished my PhD and then started thinking, and it wasn't, I'm going to say this in case people are thinking it wasn't for a lack of job opportunity. I was given a postdoc position in Hawking's own group in Cambridge. So I had that opportunity, but I turned it down. And I turned it down because I wanted to do something a bit more practical and useful with my life, the rest of my life. And I think, again, this is not an uncommon thought for people who have, gone through the PhD, maybe done one postdoc or something. Then suddenly they think, well, this is okay, but I need to be doing something that's going to have a bit more impact on my fellow human beings. And this is when they get very passionate about applying their skills into sort of, say, environmental sciences. And the problem at the moment is that it's relatively hard for those people to switch fields. Once you've done a few years of postdoc, you tend to be, particularly in the academic community, you tend to be rather, typecast. You are a string theorist, or you are and if people leave the field or want to leave the field, they're often perceived, oh, well, they must be doing this because they failed in their original field. They're just desperate to find something else as a sort of second best. But that's not my experience. It's certainly not my personal experience. And I'm finding it now a lot with the sort of postdocs who apply for positions in my group in Oxford, that they genuinely are motivated at this stage, in their, could be mid to late 20s or something, or even early 30s. They're now motivated they had a successful career, but they're motivated to do something that's going to be a bit more useful for their fellow human being. And we need somehow a system that can accommodate that type of change. These days we're all living longer. We have productive lives much longer. It's no longer the case that you're burnt out as a theoretical physicist at age 30 or something. We all have productive lives much later in life. And there's no reason why we shouldn't be able to change fields later in life. I have to say, I'm on one of the committees that the Eric Schmidt organization runs to actually fund this type of sort of people changing field late after PhD. And I think this is a great scheme, but it needs to be broadened more generally. And I think research councils and agencies and things, around the world need to be taking this into account. There's an enormous pool of talent in very sort of theoretical subjects that are really keen to apply their techniques to, for example, environmental science. But we need to be able to give them a year of, to retrain, to learn some of the jargon and that sort of thing, for them to be productive then in research grants. So I've just said that's my little bee in my bonnet about this sort of stuff.
I completely agree with that. I think a little bit later in life is the right place to focus our efforts. So people who are post PhD or post one postdoc or something who want to transition, setting up, maybe 5-year fellowships for those people so that they can really make a go of some other discipline, I think would pay off enormously in the long run.
Yeah, that's right.
Don't you think this is a general trend that, a lot of people were interested in physics and mathematics when they were younger, at least 30 years ago, is very trendy and sort of status driven to be focused on very theoretical questions. But it seems like the new generation is much more practical than perhaps we were initially. So, I think back to my mathematics education, and I took no statistics, no probability. Took a lot of very abstract mathematics that basically proved not to be useful to me or anyone else. If I could do this again, I would focus much more on applied mathematics and statistics, which I think many people realize has wide application.
Yeah, I understand what you're saying, but you're saying that with the hindsight of kind of adulthood and maturity and things. And I think that it's still the case that the very brightest, undergrads and things, as they come to think about what they want to do for PhDs, will go for those, let's say, more abstract, theoretical stuff, because it is, it is unquestionably fascinating. But the question really, as I say, that faces you in a very kind of existential way once you've come to the end of your PhD and you've got a little bit of that, you've had a crack at those sort of abstract problems, is this what I want to be doing for the rest of my life? And I think that's where people today are realizing, in the old days, those people, they might go into defense or they go to to Wall Street or some bank or other. But people say, well, realizing that's not neither of those are great alternatives either. And suddenly the whole environmental issue is hitting them in the face. And they think, well, God, I can apply my talents in this area. So I think that's what's new. I'm not sure that it's that young people are necessarily thinking at an earlier age about practical issues. I just think that, although there may be some of that, but I think, we're beginning to realize we're not typecast. We don't have to, our career is not necessarily set in stone by doing a PhD. I think that's where we got to think differently, if you like.
So let me turn to the main topic that we wanted to discuss. You recently wrote a paper, Tim, which was published in the Proceedings of the National Academy of Sciences. And the title of the paper is The Scientific Challenge of Understanding and Estimating Climate Change. So obviously, because of its central importance, climate change has been a topic we've discussed before on this podcast. And one of the issues that we really wanted to drill down, or at least I, maybe Corey's bored by this, but that I really wanted to drill down on is really what is the level of model uncertainty in climate change? How good are we actually at understanding the impact of greenhouse gases, et cetera, on the long-term evolution of the climate? And your paper caught my eye because it seemed to really be focused on these issues. What is the current level of uncertainty in the existing models? What do we really need to do to get to a higher level of certainty? And also, what are the key mechanisms inside, the key physical phenomena that make it really difficult to model climate? And I was hoping to kind of get into a discussion of that, not really for, don't assume everybody listening is a physicist or a climate scientist, but I think by and large, our listeners are pretty technically sophisticated, so you don't have to pull your punches too much. But I would like to get into that discussion.
Sure.
So let me start by just reading, I think this comes from the introduction to your paper, and it'll just kind of set the tone. So you write, the idea that the science of climate change is largely settled, common among policymakers and environmentalists, but not among the climate science community, has congealed into the view that the outlines and dimension of anthropogenic climate change are understood, and that incremental improvements to and application of the tools used to establish this outline are sufficient to provide society with the scientific basis for dealing with climate change. For certain, some things are settled. And here's a list of things I think that you think are settled. We know that greenhouse gases are accumulating in the atmosphere as a result of human activity, and that they are largely responsible for warming of surface temperatures globally. We also are confident in our understanding as to why this warming is expected to be amplified over land masses and the Arctic. Likewise, we are confident in our understanding of how the hydrological cycle amplifies the effects of this warming and how warming amplifies the hydrological cycle. For these and other broad brush strokes of the climate change picture, we are increasingly confident in our ability to usefully bound the magnitude of the effects. From this certainty stems the conviction that additional warming is best avoided by reducing or reversing emissions of long-lived greenhouse gases. So I was hoping that we could unpack that a little bit. So there are several observations in there of things that we should be very confident of, despite whatever uncertainties we're going to talk about later. And so maybe you could go through those things for us.
Yeah. So the opening paragraphs of the paper were trying to make it clear that although we are somewhat critical of the current state of climate modeling around the world, we are not in any way, doing it from the perspective of somebody that wants to attack the basic science of climate change. So we're just trying to lay that out pretty clear at the beginning. So what do I mean by that? We there's no question, as you say, that greenhouse gases are increasing, greenhouse gas concentrations are increasing due to our emission of fossil carbon. And we have no doubt that is causing a warming of the planet, and that much of the warming that we've seen over the last century or so can be attributed to those emissions of greenhouse gases. And indeed that certain aspects of the water cycle can amplify the direct effect of increases in carbon dioxide, and in particular the so-called water vapor feedback. In other words, that as the atmosphere warms, the air comprises more water vapor molecules, gaseous water molecules, and those are an additional greenhouse gas. That's an additional greenhouse gas, which then amplifies the signal. So, if you say, that has the world warmed and has it been caused by us, we would say unquestionably yes. But society needs to know more than that. There are two important issues facing us. One is how warm will it get over the next 100 years, let's say, or to the end of this century? And secondly, what does it mean in terms of local weather? How does the weather over the UK or the US or any other part of the world, how is that going to change as the global temperature rises? And what I mean by that is in terms of, storminess or drought or, rainfall amounts, whatever, intense windstorms and so on. How are the frequencies of these things going to change? Now, we typically look to our models, to our computer models, which are, essentially our best way of applying the laws of physics to the problem of climate change. So the computer models are, mathematical representations of the laws of physics. This is an important point, by the way. They're not just somehow, kind of equations made up out of thin air. They are based on for example, the fluid dynamical laws called the Navier-Stokes equations, which are representations of Newton's laws of motion, that sort of thing. So the models are our best way of solving the laws of physics. And we use them to try to get at both of these questions. A, how much will global temperature increase by, over the next 100 years or so? And secondly, what is the manifestation of that warming and that climate change to local weather patterns?
Right. So,
yeah.
Oh, sorry to interrupt. Go ahead.
Well, I can keep talking almost infinitely long, so it's probably best you interrupt me from time to time. Otherwise, I might drift off in the wrong direction.
Yeah, I just want to unpack two points that are made in your opening paragraphs and just try to maybe have you give some intuition to our listeners about them. So one of them was this reinforcement between warming and what you call the hydrological cycle and vice versa. And you may have already said that, but I just wanted to make sure I caught it, that you're talking about water vapor. So warming causes more water vapor to be in the atmosphere, and water vapor itself is a kind of greenhouse gas.
That's correct. So there are actually two elements to this. The one is what you just said, which is water vapor is a greenhouse gas. So as the atmosphere warms, it will be amplified by the presence of water in the atmosphere. This is one of many so-called feedbacks, which we may come on to, which make predicting climate change difficult, because it's not purely just a matter of how much does the carbon dioxide warm the planet. It's what extra effects are going to amplify that. And water vapor is one such amplifier. But actually that's something there's very little uncertainty about, because water vapor is, the atmosphere, unlike clouds, which we'll come to, which are sort of the liquid or ice form of water. Water vapor is fairly uniformly distributed. It doesn't vary so enormously compared to clouds. So we have a pretty good idea that the water vapor feedback is a positive one. But just before we come to the end of that question, there is a second point, which is that as the atmosphere holds more water vapor, so storms, when they form, the intensity of a storm is very frequently determined by how much water vapor condenses into liquid water and releases latent heat latent heat from condensation of vapor into liquid form. Everyone's aware, I'm sure, when a hurricane makes landfall and then goes inland, a lot of the driving water that drives the latent heat release, which drives the circulation patterns, gets shut off because the air is no longer being fed directly by such moist air from the sea. So that's a manifestation of how the intensity of storms are very much determined by the amount of condensation of water vapor to liquid water. And basically, as a general comment, that as the atmosphere warms and holds more water, so these storms will become more intense because the amount of water available to condense into liquid water is larger. And we've kind of seen that, I think, in terms of the statistics. Statistics of extreme weather events is very difficult if you take one particular location. But averaged over the whole globe, we see a tendency towards these sorts of storm systems becoming more intense. And that's consistent with this general notion that as the atmosphere holds more water, then the intensity of storms that are driven by the condensation processes increases. So that's a very general comment, but that doesn't tell you exactly, what will happen to the weather over California or over, southern UK or something like that, which is much more specific.
There's a statement here about specifically knowing that the feedback effect is positive from water vapor. and whether we know the sign of the totality of all the feedbacks, so clouds plus water vapor plus perhaps other things, do we have confidence about what the overall size of these feedback effects are relative to each other and what the overall sign is?
No, we don't. And that's one of the big problems, that when it comes to clouds, you don't have to look very far. And so when you look to clouds, then it's a much more complicated problem, and one that we have estimates of, but I would say the estimates have big uncertainties in them. So let me just say a little bit about clouds. So clouds actually can have a kind of a dual role. When you have very thick clouds, which just sit, I don't know, a kilometer or so above your head, or even lower, as everyone knows, they basically reflect the incoming solar radiation, the sunlight, back to space. So they're very reflective at the top of the cloud layer, and they shield all that sunlight from the surface. So the surface will typically be cooler when such clouds are around than when they're not. On the other hand, if you take the very thin, what are called cirrus clouds, which exist at much higher altitudes, 10 kilometers or more above the surface, they are typically much thinner, and they contain mostly ice crystal clouds rather than water droplet clouds. And they play a role in actually a bit more like a greenhouse gas of trapping the infrared heat whilst being relatively transparent to solar radiation. So a kind of worst case scenario for climate change is that if these high level clouds become more prevalent and the low level clouds dissipate, then this is going to amplify the basic climate change signal. If clouds do the opposite, the clouds amounts increase at low levels and decrease at high levels, the effect will be the opposite, and clouds will be a kind of damping effect on climate change. Now, most models actually suggest, unfortunately, that the cloud feedbacks are probably positive, which means the way the clouds adjust to the warming signal is such as to amplify that warming further, which is bad news for society. But our view is that the uncertainties in these estimates are really, really big, because we just cannot even start to resolve the dynamics of clouds with the current generation of climate models. All we can really do is say that there is certainly a risk, a fairly quantified, well, and I'm not sure how easy it is to quantify it, but apparently a substantial risk based on current generation models that the cloud feedbacks are positive. But, it's such in my view, it's such a kind of a fundamental question, because it's almost, this is how our species will go. I mean, if cloud feedbacks are very substantially positive, then it really becomes, climate change becomes an existential threat for large parts of society, particularly those living in parts of the world where temperatures can easily exceed 50 degrees Celsius and 95% humidity. I mean, once you get up to temperatures like that, the human body just cannot physically exist anymore without going to an air-conditioned room. So the only possibility is to migrate polewards.
So Tim, I'd like to come back to clouds in just a moment, but I want Corey to have an opportunity to get in here.
Sure. I just like to go to the second level of your model, which is the water vapor effect. So can you give us an idea of the magnitude of the effect of feedback on increased water vapor? What do we know about that?
Yeah, well, I mean, if you double carbon dioxide and only take the carbon dioxide only into account, then you're talking about a warming of about 1 degree or so for a doubling of carbon dioxide, 1 degree Celsius, 1 degree. Yeah. The water vapor can double that. So we're talking 2 degrees or so. And then the clouds on top of that can change it, can even double that again to 4 degrees or more. So that's, these are substantial effects. I mean, this is not new physics. It was understood back in the 19th century, I think, by John Tyndall, that water vapor, in fact, in some ways, water vapor is the most important of all greenhouse gases. A molecule for molecule, it's more important than carbon dioxide. But of course, what we're doing with carbon dioxide is systematically increasing it by our emissions of fossil fuels. But the water vapor is kind of tagging on the back of that by increasing through that effect.
Would it be fair to say that uncertainty in the CO2 effect, say 1 degree Celsius per doubling, that uncertainty could be low, like 10%-ish uncertainty. Water vapor, maybe you could tell us what kind of fractional uncertainty in that number is. And in clouds, you said it maybe could be even 100% or 200% uncertainty in the prediction.
Yeah, I think that's right. I'm not really aware that there's any substantial uncertainty in the carbon dioxide quantity, because it's, well, with one proviso that, when we do these climate projections, we have to assume that we know how the emissions of carbon dioxide will be changing over the next 100 years. So, the way to do that, the way that's typically done in these IPCC assessment reports is that everybody runs the same, what are called scenarios, where the carbon dioxide increases at a certain level, which would correspond to so-called business as usual, where we take no action to mitigate, or others where we invoke substantial emissions cuts. But given a scenario in a prescribed scenario of how carbon dioxide is increasing with time, then the uncertainty in the direct radiative response to that increased carbon dioxide is tiny. I think more like 1%, I would say, rather than 10%. When you're talking about water vapor, there is some uncertainty about how water vapor distributes as a function of latitude, but it's not a very large number. Again, perhaps 10% is a ballpark. But you're right, clouds is 100%. We just don't know at the moment which direction the cloud feedbacks will go. I have to say, most models do say it's positive, but it's not easy. The problem, this is an area where you can't just write down a simple back of the envelope calculation and say, well, this is the way it should go, so the models have to kind of follow this. We just don't know. The mechanisms are so complex and interactive.
I just wanted to ask one more thing about these opening paragraphs that I found interesting. You say that warming is expected to be amplified over land masses and the Arctic. And I've read this in other climate papers, but I never understood whether, is that an empirical result, or is there in that case a simple back of the envelope argument that lets you know that would be the case?
Yeah, that's more of a simple back of the envelope calculation. Most of the heat when the sun shines over land is, absorbed in the top meter or so of the land surface. Very little diffuses down, at least on terms of the time scale you're talking about, but not so much diffuses downwards over tens or hundreds of meters. But the ocean, you've got circulations, which where warm water that's been warmed at the surface then is abducted down below the surface and mixes deep down. So effectively, the warming over land, the warming of the air, if you like, or the warming of the surface, perhaps is a better way to put it, over land is pretty much, restricted to the top few meters, whereas in the ocean, it's transported down over many, potentially hundreds of meters or more. If you mix a certain amount of heat over a big amount of mass, the increase in temperature, the mean increase in temperature will be smaller. So that's why the temperatures increase more over land than over the ocean. So it's not all we're saying in that paper is it's not a profound statement to say that we understand why, which indeed is what we see observationally, why the warming is larger over the continents than over the oceans.
Yeah. So I have a question about water vapor. And I'm wondering, is this increase going to begin at the surface of the Earth? So overall, it will lead to higher humidity across the planet? And if so, what percent increased humidity are we looking at? And have people really looked at the effect of having higher humidity, not just higher temperatures, on effectively human survival? Because I think everyone knows it's much harder to operate in 90% humidity than it is in 20% at high temperatures.
A way that we can measure these things is through relative humidity. And what we're seeing is that as temperatures increase, the relative humidity of the air is staying roughly constant. So that means the absolute humidity is increasing at the same, if you like, rate as the temperature is increasing to make the relative humidity constant. The warming effect, I should say, from increased water vapor, though, arises where the relative humidity is increased through a column of the atmosphere in the vertical. If you just had relative humidity only being larger at the surface, that actually wouldn't have such a big effect. It's actually the fact that humidity has increased right through the depth of the atmosphere. But as far as the sort of physiological effect on humans is concerned, you're absolutely right. And there have actually been a few papers on this in recent years where people point out, as you correctly say, that it's not, the effect on the human body is not just from temperature. It's a combination of temperature and humidity. And there's a thing called a dew point temperature, which is sometimes used, which sort of combines temperature and humidity in this way. So you can say when the dew point temperature exceeds some threshold, whose value I now forget exactly what that value is, 38 degrees or something, that, you get to the stage where, as I said before, you can get heat waves where the human body actually just can't lose heat. It means you can't sweat. You can't lose heat by perspiration, never mind by direct sensible heat loss. So that becomes, as I say, an existential threat to human life. And we've had situations like this in the last few years in parts of the world, particularly in the Middle East. I think parts of Iran and Iraq have experienced these sorts of conditions for a few weeks, which are really very close to this combination of high temperature and high humidity, where it's impossible to lose heat. Even sitting in the shade, you can't lose heat. And if this becomes more widespread around the world, which it certainly is projected to do, that becomes a real problem, because what do people do then?
So Tim, let's suppose the cloud dynamics are very disfavorable to us, so they yield a large positive feedback effect for climate change. Would we have seen that in the geologic record? So would there have been times when the climate ran off due to that effect and other things, and would we know about it?
I mean, I'm not a great expert in paleoclimate, but there are certainly periods of time where the temperature has risen enormously, and people certainly have speculated that this must be due to positive cloud feedbacks occurring, because there's no other way to sort of understand how these enormous shifts in paleoclimate can occur. And of course, the mother of all examples of, positive feedback is Venus, which has this so-called runaway greenhouse effect, which you can view as a kind of a sort of the ultimate in positive feedbacks, where you now got temperatures of hundreds of degrees, which obviously, I don't think people are, in fact, people aren't suggesting that the Earth is going to turn into a Venus exactly, but it just makes the point that really, to understand the greenhouse effect and to understand climate change, it's more than just understanding the kind of radiative effects of carbon dioxide. And let me just bring this right up to date, because right now people are putting the final touches to what's called the sixth assessment of the IPCC, the Intergovernmental Panel on Climate Change. And I think the report will be released next year sometime. And for the last few years, modeling groups around the world have been doing their, projections with their latest versions of the models to get the latest estimates of global warming. And over the last few years, most models, or I say a significant number of models, have actually revised some of their cloud, what are called parameterization. So I come back to this point that the clouds are not represented, if you like, explicitly in the models with the law, the fluid dynamical equations. They're represented by somewhat simplified formulae, which attempt to describe the effects of clouds and the interaction with the circulation patterns in a sort of simplified way. Anyway, these models, there's been a kind of a fairly widespread revision of some of the particular details of how much certain types of clouds have, how much of the cloud is made of water and how much of the cloud is made of ice crystals. Now, the thing is, it turns out this is quite a subtle effect, because most clouds, the actual ambient temperature in the cloud is well below freezing, is well below 0 degrees. But the cloud liquid water is often in supercooled water droplet form, and that it needs some, aerosol impurities or whatever to change it into ice. And so this question of what is the balance between supercooled water droplets and ice droplets is quite a tricky one to represent correctly in these climate models. But anyway, a lot of the climate models have undergone some revisions to these what are called cloud microphysics schemes. And it seems that the ones that have undergone this revision in terms of containing more supercooled water droplets than previously are now producing much bigger cloud feedback effects, which is a kind of complicated thing to understand, but people are trying to do that. But the point is that a lot of these models now are producing amounts of warming to a doubling of carbon dioxide that were not seen in any of the models that occurred in the previous IPCC report. So we're going to find in the sixth assessment report a number of models where the projected increase to a doubling of carbon dioxide will be over 5 degrees, 5.5 degrees or more, whereas previously the maximum was only around 4 degrees or 4.5 degrees. So this represents a considerable shift in this latest report to this warming, to this, rather, I would say, I hasten to use the word catastrophic, but it's kind of, verging on a really serious movement towards the warm end of the spectrum from our human emissions.
So I think the viewpoint you take in the paper is that to really resolve this cloud microphysics, we need a more granular grid size in simulations that maybe really even take into account Navier-Stokes evolution in the atmosphere. Absent that, how confident can you be in, say, the sixth IPCC modeling, sixth version of the report modeling that gives this increase in temperature increase per CO2 doubling?
Well, I don't know how to put a level of confidence on it. All I can say is it's our best attempt at applying the science of climate change to the problem of climate change, given our understanding of the science, which actually is pretty good. Because most of the physics of climate change, it's not all of the physics, but most of the physics is kind of 19th century physics. It's to do with thermodynamics and fluid dynamics and, stuff that's pretty well understood from a theoretical point of view. The problem is that we can't solve the equations as accurately as we would like. So, when the sixth assessment of IPCC comes out, I'll say this is our best attempt with this, given our science and given the tools we have to do the science. But, my view is that this modeling issue is so important that we're not putting nearly enough in the way of resources to try to understand and be more confident about some of these feedback processes. And I should say, by the way, that, the models are not just used. I mean, we've talked a lot in this interview so far about global temperatures. How much will global temperatures rise? And I'm saying the latest, stuff is 5 degrees, which is a lot. But what affects people on the ground is not global mean temperature. It's what the weather does. It's like, how many fires you're going to get in California or in Australia, how many intense tropical cyclones are going to hit Mozambique or the Caribbean or wherever, how many droughts are going to affect Somalia or, other countries in the sub-Saharan Sahel. How many windstorms are going to whack into southern England or whatever it is. So these are the practical questions. The UK's had some terrible floods from severe winter storms, and knowing how much money to invest in flood defenses, because of climate change is important. Knowing how to manage the forests under climate change in California and Australia is important. So having better models is not just about having a better grasp on what the global mean temperature increase is going to be. It's actually having a much better handle on how the extreme weather events are going to evolve at a regional level. And in a way, I feel that is the crucial point because, we've got to cut our emissions anyway. But on top of that, we've got to think about how do we invest in infrastructure at the regional level to, adapt to things that are going to happen anyway. And how do we spend that money effectively? And we don't spend very much money actually on climate modeling. I mean, compared to what we spend on, putting space, instruments into space, either looking at the Earth or looking at the stars and things, there's a lot more than we spend on modeling and computing.
Yes. So, the way I would say it is if you're making what are effectively $1 trillion or even existential societal decisions, investing $1 billion on better simulations seems like a reasonable investment. And it's, as you say, it's even cheaper than gathering observational data on this problem. Now, I think correct me if I'm wrong, the current grid size for these simulations is kind of on the order of 10 kilometers cubed. Is that fair?
No, that's not quite right. I mean, if you take a weather forecast model that runs out to, just 10, you have to do a 10-day forecast every day or something like that, then yes, about a 10-kilometer grid or even actually a little bit less sometimes is what's possible. But most climate models tend to have rather coarser grids than that. In fact, this is the problem, that a lot of the models that go into IPCC are still almost kind of associated with university groups, and they don't have a lot of resources for models or, computing things. So they end up being closer to 100 kilometers. So you get quite a spectrum of resolutions. The best ones are maybe down to 20 kilometers, but many of them are up at 100 kilometers or so.
Right. So imagine you have some very nonlinear Navier-Stokes evolution happening in 100 kilometer by 100 kilometer by, I guess the height would also be something like 10 or 20 kilometers, right? That you have to model out to.
No, the height tends to be, because the atmosphere is a very thin layer compared to, if you take the Earth and imagine the atmosphere as a layer, it's just a kind of, it's a tiny amount of thickness compared to the radius of the Earth. So the models would have, the best models actually would be in tens of meters of resolution, but the worst ones maybe a kilometer or so.
Okay.
Tim, part of my role is as the audience ombudsperson to flag terminology that people may not be familiar with. So Navier-Stokes, can one of you please give us a simple description of?
Sure. Navier-Stokes. I mean, I'm pronouncing this word Navier like a typical Anglo person that I am. I mean, Claude Navier was a French scientist who actually, I think, to be honest, he actually predated and independently of George Stokes, who was an Irish physicist. So Navier, French, Stokes, Irish. They both basically wrote down an equation which was a kind of a manifestation of Newton's second law of motion. So Newton's second law of motion is force equals mass times acceleration. I mean, Newton, when he wrote down those laws, was thinking of applying it to a planet. So you have a single solitary object, which you apply the force of gravity to, and the object accelerates under the effect of that gravity according to force equals mass times acceleration. The problem with a fluid like the atmosphere or the ocean, fluid can be a liquid or a gas, is that effectively you have an infinity of little particles that make up that fluid, if you like atoms or something like that. So how do you represent Newton's laws of motion applied to that whole fluid when it comprises an infinity of particles? And what Navier and Stokes, as I say, independently realized was you could use the language of calculus and a thing called a partial differentiation to write down a single. Now, so this is a good question, because what you can do is you can write down a single equation using this language of the partial differential calculus, which expresses Newton's second law, force equals mass times acceleration, for this infinity of little tiny atoms that make up a fluid, like a liquid or a gas. So as an equation, it's incredibly beautiful. It's a beautiful piece of mathematics. And in fact, even to this day, groups, in applied mathematics departments, try to understand the theoretical mathematical properties of this partial differential equation that we call the Navier-Stokes equation. The problem with it is, if you actually want to solve the equation to get numbers out, you've got to go back down and break it up into these, little atoms. And that's where the problem comes, that when you have a computer of a certain size, you're given a computer, here's a computer, so solve the equations. The first thing you have to do is say, okay, how small can I break my fluid up into pieces, if you like, into these sort of atomistic pieces, which will allow me to make a projection of the equation. Say I want to run the model out for 100 simulated years. You say, well, I can't if it takes me 10 real years to make 100 simulated years, I mean, then I'm going to be waiting 10 years to get any answers out. So that's no good. So you say, well, okay, 100 simulated years, I could maybe wait a month, I'd say. That might be a kind of calculation people would say. I can't wait more than a month to get that 100 simulated years. So that determines how big, or how small, I should say, how small your atoms are, the kind of numerical atoms that you go back to actually solve the Navier-Stokes equations. And that's where that's when I say most models, climate models, have these grids of 100 kilometers. It means that the kind of atoms, I mean, the word atom I'm putting in quotation marks because they're not real atoms, but they're just sort of, it's a discretization of this fluid into chunks of size 100 kilometers by 100 kilometers by maybe 1 or 2 or something kilometers in the vertical. That is the smallest they can go in order to produce 100 simulated years in a month.
So I guess to summarize that a little bit. So you have these nonlinear partial differential equations, which describe the evolution of this fluid.
Correct.
That we care a lot about. And, solving these equations is remarkably hard. I even see papers where you might have a theorem, which some mathematician actually proves about, rigorous behavior of Navier-Stokes equations. That would be could be a new result. You could have a result where some people simulating on a supercomputer actually managed to reproduce some patterns that you see in your coffee cup when you pour cream into the coffee. That's a hard problem. So now imagine that I want to figure out what is the distribution of clouds, ice crystals in the clouds, and supercooled droplets of liquid water in the clouds up to an atmosphere of, up to a height of, multiple kilometers at least. And I'm not able to do this with current computing power. And so I actually subsume all of that complex physics, which is highly nonlinear and it's chaotic and it involves turbulence. I subsume that into some simple equation, which just says, hey, if the temperature and the pressure and some other parameters within this huge cell, which is 100 kilometers by 100 kilometers, is this, then the distribution of clouds and the consequent reflectivity at the top and the infrared screening at the bottom, it is that. And supposedly my little summary of all the complex stuff in just these simple equations is what turns out to be maybe the biggest uncertainty in the evolution of the bigger climate model. I think that's the problem these people are confronting. Is that fair?
That I think you summed that up reasonably well.
Tim, so I want to come back to 2 points you've made. One question is, we commonly say that climate is an existential risk, but of course it's relative to location. I don't think that parts of Canada are going to suffer that catastrophically from even a 5-degree temperature rise. But that's existential for Sudan or Iraq. And I think this is related to your observation that we don't invest a whole lot of money in climate modeling, because perhaps the cynical side of me says, look, the people with the money to invest are actually not facing existential risk. They're facing inconvenience. But the places that are really in danger of having the population wiped out don't have the money and are often complaining the loudest, but their desires aren't being heard. So what do you think about that? But first, I'd like to hear your take on, you talked about we want to know the effect of weather in different parts of the world. Can you give us a little bit of a survey, what you, from your studies, you think might be certain effects in different parts of the world, and then your reaction to my take on perhaps what's motivating people to invest or not invest in commodities?
Well, look, can I attack? Let me. I'll tell you some things about specific parts of the world in a minute, but let me, because I have a sort of a slightly funny story about that. Well, you may not think it's funny, but anyway, I'll tell it anyway. But let me just first come on to this point about existential. So I think you're right that, the citizens of Canada are probably not going to face existential threats directly from climate change. But I make 2 points. One is that sea level rise will affect everybody. So any low-lying, coastal cities, I don't know whether Vancouver would count as one, but any low-lying coastal cities faced with potentially meters of sea level rise. Again, by the way, that's another one of these massively unknown quantities, because we can calculate how much the sea level will rise directly from the thermal expansion of the water as it warms. What we can't figure out very well is whether the ice sheets over places like Greenland and parts of Antarctica will not so much melt, but will disintegrate, will actually dynamically collapse. We just don't know that. So that makes all the difference between sea level being, a meter higher or several meters higher. And that makes a big difference for a lot of coastal cities. The other point which I want to make is I kind of maybe vaguely alluded to it. If you're, bearing in mind that most of the population rise over the next decades will be in developing countries, large parts of Africa and so on. If these people are facing, themselves existential threats, then they are going to, as humanity has always done for, thousands of years, when the climate's got bad, you just move. You move somewhere where it's a little bit more equable. And that basically will mean moving poleward. So, in Europe, we've seen problems from migration from countries facing, increased climate threats. And I think in the US as well, you've seen something similar. I mean, this is probably nothing compared to what it could be like by the middle of this century. So again, a massive uncontrolled migration polewards may not be an existential threat for the, average Canadian, but it's something which, we need to start dealing with now rather than waiting for it to happen. I would say at the moment, this is trying to be confident about how climate change will manifest itself regionally. It is a problem that, again, where a lot of uncertainties. But I remember some years ago, I was being interviewed this is actually for a government position, where there was a lady from the Scottish devolved administration. And she asked me, well, what will climate change be like in Scotland? How, that's right. It wasn't so much how will climate change. What are the main health threats from climate change? Now, I'm sure she was dying for me to say, oh, well, there'll be massive incidents of skin cancer and heat stroke and all this sort of stuff, as Scotland becomes this kind of new Mediterranean type of country. But, my experience is that actually what will happen in a place like that is that and we were talking about this earlier, the increased humidity in the air will just make cloud cover for that part of the world relentless. So it's bad enough in the winter when the daylight hours are very short anyway of seeing the sunshine. My own view is that with climate change, you'll never see the bloody sun in the wintertime. And so the biggest threat, I would say, health-wise, is not heat stroke and skin cancer. It's kind of depression, alcoholism, and drug abuse. And also vitamin D deficiency, rickets, that sort of thing. Those are the big health threats. So all I'm saying here is that, these things are very, very subtle issues and quite complex issues. And a big problem for the UK, my own experience is that we have had a number of very wet winters, and there's a lot of money going into investment into flood defenses. But unfortunately, what I don't see, and I think people haven't quite kind of realized this, that they think very much climate change is a kind of a trend towards some, in some direction, like towards a wetter climate. But what we don't know is whether, in fact, the kind of extremes of climate will increase. So it's not, there'll be a trend, but there may also be an increase in the variance. So the thing is, what happens if there's an increase in winters or indeed whole seasons where high pressure, what are called blocking anticyclones form and persist? Because then what will happen is we'll run out of water, we'll have no renewable energy because the sun doesn't shine, the wind doesn't blow in a wintertime anticyclone. And these are actually often situations where the air temperature can be quite cold, so the demand for electricity can be quite high. So, planning carefully for our energy needs in the future, really requires us to answer these questions quite carefully about not just is there a trend towards wetter winters, but how are the variants of these types of extremes going to change as well? Or are we going to get more of these extreme high pressure winters, which would have the opposite effect, where we'd run out of water, we'd run out of renewable energy and stuff like that? Anyway, all I'm saying is these are unbelievably complicated questions, and answering it from a model that's just been written, by a small group of people at university to answer a few kind of hypothetical, very large scale kind of questions about the physics of climate change isn't good enough. We need to be developing models, putting massively more investment into them than we currently are if we're going to really answer these important policy and societally important questions.
Tim, have you ever heard of Richard Weller?
The name is familiar, but just remind me.
So he's a dermatologist from Edinburgh, but he's done a lot of research on the effect of sunlight on cardiovascular health. It looks like getting too little sunlight is a risk for cardiovascular health.
I can believe that. Yeah,
he's got a talk called on YouTube, which you can find, called "Why the Scots Are So Sick."
Yep.
And so it's generally known that rates of cardiovascular disease go up with latitude.
Yep.
And a bunch of Scandinavian studies have supported this also. So I think one of the consequences of a very, very cloudy Scotland is even higher. Scots already have the highest rates of cardiovascular disease in the UK. Yep. At even higher rates as a result.
Yeah, it could get worse. I mean, this is the sort of thing that could get worse. And people aren't, thinking on those lines. They're always thinking of climate change as something, if it's warmer, it must be, we're going to lots of sunny days and sunny skies and everything. But it doesn't necessarily work like that.
Yeah, to your question though, Corey, I mean, it is true that maybe in the global north or the economic north, it isn't an existential problem, or maybe most of the risk is not existential, it's more economic. But still, the amount of dollars or pounds that are at stake is so high that the amount of investment in sort of better computing to try to get better answers it's kind of criminal how little investment. It's equivalent to us knowing that a viral pandemic was a possibility and we've been talking about it for 20, 30 years. And when the thing actually arrives, we're totally unprepared. So I think it's that hopefully people will learn from the crisis that we're currently in.
No, I mean, I often say it's a matter of investing $1 billion or so, which, $1 billion sounds a lot. But on the other hand, $1 billion is what you spend on a single space or something like that. It's
or even on a small particle collider. Actually,
I mean, it's one, was it a year's worth of the CERN budget or something? Just finish off this point about, I make the analogy sometimes with the Marshall Plan, after the Second World War, that the US basically, kickstarted the European economy after the Second World War through this massive injection of cash called the Marshall Plan. And, I'm sure a lot of people like to think of it, and I'm sure it was to some extent an altruistic gesture. But everybody recognizes that the US had an ulterior motive, which was to prevent Europe becoming a communist continent. It was a way to, get the capitalist system working again and to prevent communism taking over. I see, trying to understand climate change in the developing world and to maybe invest in the sorts of infrastructures that will make society there more resilient to changes in extreme weather. And that would include better warning, early warning systems, to be kind of a part of a modern day Marshall Plan. And what you're trying to stop now is a kind of, as I say, an uncontrolled migration of people from these places by, say, the mid-century, because it's just become unbearable there. So I think there's a good parallel with what happened after World War II that's worth contemplating.
Steve knows this quite well. I'm a little cynical about human ability to react in the absence of crises. And so we're seeing it right now with the pandemic. We're putting in, it's going to cost us a couple $1 trillion probably over the course of this. And right, it could have been mitigated definitely with $1 billion or so of investment. But I think, you are seeing much more discussion of these topics as you see migration pressures, but it's really an open question what it'll take to move policymakers, how much crisis at the border. Not a great history. World War II had to happen, and then you had the Marshall Plan.
Yeah, no, I totally agree with what you're saying, but nevertheless, we have to say it.
So, Tim, are there large funding sources that are becoming available for this kind of simulation? Are you optimistic about where we'll be, say, 10 years from now in terms of the quality of climate models?
I mean, in Europe, we have the European Union, and a group of us. We have a project called Extreme Earth, which I would encourage any of your listeners to check into the website, extremeearth.eu, I think it is, or something like that, where we're trying to engage with the European Union to fund this type of project in Europe. Climate adaptation is definitely a high priority item now in the EU. So I'm moderately hopeful something like that will happen. I mean, I'm in the unfortunate situation of now belonging to a country which is leaving the EU, which is not helpful very much. I'm in the slightly fortunate situation where my mother was Irish, so I actually have an Irish passport as well as a British passport. So if the worst comes to worst, I'll move to Dublin and set up shop there and carry on with my EU connections. But we're waiting to see how the EU negotiates. How the UK and the EU negotiate. I mean, there is a chance, if things work out well, that we'll end up like Switzerland or Norway, which is we're not formally part of the EU, but we still have all the kind of scientific connections to the EU through these framework programs and now Horizon Europe programs.
Well, I'd like to tell you a sort of hopeful or optimistic story from my own 30 odd years in physics. There's a simulation project called Lattice QCD, which is this incredibly difficult computational problem of simulating the dynamics of quarks and gluons inside of protons and neutrons and nuclei. And this is a super nonlinear system. It's actually highly quantum mechanical, but the basic equations are known. The basic equations are almost as simple in a way as Navier-Stokes equations, but take incredible resources to solve. When I entered the field, there was no hope that we would ever solve and derive from first principles the properties of protons and neutrons and other strongly interacting nuclear particles from the properties of quarks and gluons. But over 30 years, through just incredible effort, both theoretical effort and also just better and better compute, we finally can extract precise predictions about things like nuclear electric dipole moment of the neutron or mass of the proton or the pion from first principles, from quark level stuff. So, it's one of these things where if you look at a cloud directly, it doesn't seem to be changing very much. If you look away and look back again, the cloud has changed tremendously. And in the case of Lattice QCD, that's what happened. These guys this distributed group of people all around the world worked on this problem for 30 years and eventually kind of solved it. And I think the same thing could happen with climate. So you should just keep up hope and keep pushing, even though the problem itself is super hard.
Yeah, I agree with that. And I think there is hope. Let me make a comment that's maybe slightly more relevant to the US, which is that, I think we have actually achieved some remarkable things in Europe through the European Union. And essentially what it's meant is that, countries of Europe have come together and kind of pooled resources and done things that individual countries could not have. And I think there's a parallel here in the US, at least from my field of climate, that there are all these federal agencies like NOAA, the National Oceanographic and Atmospheric Administration, NSF, DOE, NASA, Department of Defense, and so on. They all have their own kind of semi-independent capabilities in this climate area. NASA has a climate model because it likes to sort of compare their space observations with simulations. NOAA has stuff to do weather forecasting, and SF has labs in Boulder that do, climate prediction things. DOE have their own climate models. I think to make progress in this area, this is a problem where the agency should actually come together and say we can actually do better if we join forces and create some new generation climate model where, maybe different agencies focus on different aspects of the problem rather than trying to invent the wheel each time themselves, which I think has been kind of wasteful of resources. I think it would be better to actually join together and have a concerted effort in America on solving this problem. I think that would really advance the science massively. That happened.
I agree with you. I think probably the problem is just this kind of interagency bureaucratic friction or competition that prevents this kind of thing from happening. But I agree with you. If they pooled their resources, they would get much more bang for their buck.
Absolutely. Yeah.
It's really been a pleasure talking to you, Tim. And I think our listeners will have a much better feel actually for the actual scientific problem of the modeling climate after listening to this.
Well, it's been a pleasure to talk to you, and hope we come back in a few years and we'll see how things have progressed, hopefully in the right direction.
That would be great. Thanks a lot for your time.
Okay.
Thank you, Tim.